Okay, so we're moving on through chapter 6, so let's get right to it. This is section 6.5, where we take something similar to the previous section where we learned about graphs of sine and cosine, and we apply them to all the others: tangent, cotangent, cosecant, and secant. We're going to go through this section fairly quickly. It's not as heavily stressed as the other ones. Okay. So the basic objectives are to graph various forms of tangent, cotangent, and so forth. Okay. So let's just take a look right at the tangent function. Okay, so we have some nice reference values. We know, for example, that tangent of negative pi over 2 does not exist. It's not in the domain, and the tangent of pi over 2 also does not exist because, remember, tangent is sine x over cos x, and cosine has zeros there. These are actually vertical asymptotes of the graph. Okay. And here are the various reference values we've already computed in between negative pi over 2 and pi over 2. Okay, it's also an odd function, which means it has this symmetry around the origin, so we have this sort of reflectional symmetry. Now, as x gets closer to pi over 2, so in our reference circle, I'm getting really close to pi over 2. Sine is getting very close to 1, and cosine is getting very close to 0, so this does have a vertical asymptote here, and it keeps going up. And similarly, this will get reflected down here to this vertical asymptote. Okay, but it has a period of pi, which means it just starts repeating itself over and over again. So once we've determined what it does between negative pi over 2 and pi over 2, that's a total length of pi. Now it just repeats it because it has a period of pi. So this is your graph of your basic tangent function. It's weird, it has infinitely many vertical asymptotes because it keeps repeating itself over and over again. Generally, we only draw one period of it. We just draw it from negative pi over 2 to pi over 2, but hey, here's the complete graph. Okay. So the domain is all real numbers except odd multiples of pi over 2. We already knew that. The range is all real numbers. Going back, it goes all the way up and all the way down. You can get out anything you want. Okay, so going back forward. The range is all real numbers. It's an odd function, so we have that symmetry. It's periodic with period pi. We already knew that. There's a single x-intercept in that normal standard 1 period right at the origin at 0. But because it has period pi, if it has an intercept at 0, it also has it at pi and 2 pi and 3 pi and negative 2 pi and so forth. And we have already spotted these vertical asymptotes at odd multiples of pi over 2. It's exactly where you're not in the domain and you have these vertical asymptotes. Okay. What about cotangent? So instead of sine over cosine, this is now cosine over sine. So the domain of this was everything except multiples of pi. So really what we want to do is we want to graph it just in one period from 0 to pi. Its intercept is at pi over 2, and if you just plot some reference values, you'll see that it goes up here towards this vertical asymptote and down here towards this one. And since it has a period of pi, it starts repeating. So compared to tangent, tangent's fundamental shape was this, and it went through the origin with asymptotes at pi over 2. So the shape is kind of similar, but it's almost like a mirror image, and the asymptotes happen at different places. But otherwise, it is sort of similar behavior. Notice again, the range is everything. Summarized. Oh, they didn't give us a summary. Well, summarized, the domain is everything except for multiples of pi. The range is all real numbers. It's not exactly an even or odd function. Sorry, it is an odd function, but it's... So here's the origin. So it does have some reflectional symmetry through the origin. It's just a little trickier to see. It's got intercepts at odd multiples of pi over 2, and it's got vertical asymptotes at multiples of pi. So can we graph 3/2 tan x plus 1/2, and then determine the domain and range? So we're going to do our normal sequence of steps using transformations. Here on the left is our normal graph of tangent. Fundamentally, what you want is one period of it. After that, it's kind of optional, but one period of tangent goes from negative pi over 2 to pi over 2 and goes up from left to right between its two vertical asymptotes. Now, if I stretch this by a factor of 3/2, it's very difficult to tell the difference. My intercept doesn't change. My asymptotes still go to plus or minus infinity. It just goes a little bit faster. So if I remove my pen marks so that you can compare, like if you look here, versus here, it's a little bit stretched out, but I gotta say, visually, it's tough to tell how a stretching actually affected this picture. I mean, it did, it's just subtle. The next thing we want to do is that vertical shift by 1/2, which just shifts everything up by 1/2. So now that we've got this graph in front of us, can you answer questions about what's the domain and what's the range? Well, the domain is still the same and the range is still the same. So flipping back, our original tangent function had these as vertical asymptotes and went all the way down and all the way up. Stretching it vertically by 3/2 did not change any of that. It did not change where the vertical asymptotes were, and it didn't change the fact that I could go all the way down to -infinity or all the way up to +infinity. And then adding 1/2, just shifting the entire graph up, didn't change the vertical asymptotes. And if I had all real numbers as possible outputs and I add 1/2, I still have all real numbers. So the domain and range are actually unchanged from the original tangent function. How about 3 times the cotangent of 2x? So start with the graph of cotangent, and specifically a base period of cotangent goes from 0 to pi, and it goes down from left to right. So we start with that. From 0 to pi, we have 1 period. We needed to multiply by 3, and again, that's a fairly subtle thing. If it was a negative number, it would be much more visually identifiable. It would flip it vertically. Multiplying it by 3 just means, yeah, it goes up and down to infinity faster, okay? But the vertical asymptotes haven't changed, and what hasn't changed as well is the fact that the range is all real numbers. And then what did we have to do? We had to do a horizontal compression. Now that does start changing things. The original period was all the way from 0 to pi, but now that it's been scaled by a factor of 1/2, I have a vertical asymptote at pi/2. So my original vertical asymptotes were 0, pi, 2 pi, 3 pi, and so forth. But now I scale by 1/2, and my new vertical asymptotes are 0, pi/2, pi, 3 pi/2, and so forth. This horizontal compression doesn't change the range. Whatever up and down motion I had, I still have. But it has changed the location of the vertical asymptotes by making them occur twice as frequently. The distance between them is half as long. Whoops. So the domain has been changed now because the vertical asymptotes got moved. So I can't put in pi/2 or 2 pi/2 or 3 pi/2, etc. But the range is still all real numbers. Okay, as I said, we're going through this section fairly quickly. We'd really like you to focus on graphing sines and cosines like in the previous section and not get too mixed up with your cotangents and whatnot. Now the cosecant function is a little weird. It's 1 over cosine. So the cosine curve, sorry, it's 1 over sine. So the sine curve is here in black. If I do 1 over it, wherever the sine curve has an intercept, the cosecant curve is going to have a vertical asymptote because I'm trying to divide by 0. Here I am small and positive, so this goes off to infinity, but just to the left, the sine curve is small and negative, so this vertical asymptote goes off to -infinity. 1 over a small negative number is a big negative number. The maximum value that sine hits is 1, and 1 over 1 happens to be 1, so that is the minimum value that cosecant hits. So basically, the sine curve has a lot of symmetry to it, so therefore so does the cosecant curve. You've got your positive hills and your negative hills, and when I reciprocate them, I get positive vertical asymptote bounded cups and negative vertical asymptote bounded cups. Okay, the period is still 2 pi, but there is a vertical asymptote that breaks it in half. Okay. Secant is just 1 over cosine, so since cosine also has vertical hills and positive hills and negative hills, 1 over it has positive cups with vertical asymptotes and negative cups with vertical asymptotes, but it has been shifted a little bit. Because remember, we've established, sorry, previous slide, we've established, come on, go back to the pen mode, I don't know how that changed. So we've established that the sine of x is just a horizontal shift of the cosine curve. This means the cosecant is also a horizontal shift of the cosecant. the cosecant is a horizontal shift of the secant. So this secant function is really just the same thing we just drew, but shifted left by pi over 2. So try to graph 2 times cosecant x minus 1, and then determine domain and range. So first I'm going to say the period of cosecant is 2 pi, and this is unchanged here. So my cosecant curve is 1 over sine, okay? So if I start at 0 to 2 pi, the sine curve has a positive hill and then it has a negative hill, which means my curve here has another vertical asymptote at pi. And let me switch colors so that it can be seen a little bit easier. If sine had a positive hill, cosecant has a positive cup with vertical asymptotes there and coming down to this this minimum value, of 1. And then where sine has this negative hill, cosecant has this negative cup coming down to a maximum, of -1. So here is my generic curve for cosecant x. All I have to do is stretch it by 2, which means instead of coming down to 1, this cup is only going to come down to a value of 2. And instead of going up to -1, this one only goes up to a value of -2. But the vertical asymptotes haven't changed. Okay, so now I'm graphing 2 cosecant x. And my vertical asymptotes are still at 0, pi, 2 pi. And then the only thing left to do is shift this down by 1. So instead of this being y equals 2, it's going to be y equals 1. And instead of this being y equals -2, it's going to be y equals -3. But since I really haven't labeled anything else on the graph, there's not much to change. And the vertical asymptotes didn't change as well. So the domain hasn't changed because we never moved our vertical asymptotes. The domain is still all numbers except multiples of pi. The range, however, did change. The original range of cosecant was everything bigger than or equal to 1 or less than or equal to -1. But notice we've changed this. We can still get out everything bigger than or equal to 1 or less than or equal to -3. This had an intermediate step. The multiplication by 2 changed that to bigger than or equal to 2 or less than or equal to -2. But then I subtracted 1 by doing this vertical shift. So this ended up back at 1. So the range here is going to be everything bigger than or equal to 1 or less than or equal to -3. Okay, so I'll delete my really bad drawings and we'll see some nice computer-made drawings. Okay, I do like to draw them by hand just to get across that you don't need a computer to do this. There's nothing magical about the pictures the computer gives you. You can get all the same information by hand. So we start with our normal cosecant curve. Okay, I only drew it from 0 to 2 pi, so I only drew 1 upward cup and 1 downward cup. Then we scale them by 2. That does change the heights of these extremal values, but it doesn't change the vertical asymptotes, and the picture is fundamentally not that different. But then when I shift them down by 1, we get new heights here. But again, the vertical asymptotes haven't changed. So the domain is unchanged, everything except multiples of pi. But the range is now everything less than or equal to 3 or bigger than or equal to 1. Okay, so that's exactly what we found. So that's really all there is to say about this section, graphing tangent and cotangent, secant and cosecant with the same sort of shifts. So it's not hugely complicated, but I do want to stress we tend to make you focus more on sine and cosine because they're much more commonly used in applications. And if you don't know how sine and cosine work, you're not going to have much hope of getting tangent and cotangent and secant and all that. I mean, we saw that the hills of sine and cosine give us our cups of secant and cosecant. So we really want to make sure you understand sine and cosine first. So if you are not 100% rock solid on section 6.4, the previous one, go back and practice that before you start miring yourself in the problems out of section 6.5. The previous section was much more important than this one, which is why I squished this all into one video.